Hi, my name is Olivia Shawy, and today we will be going over the basics of linear approximation. The concept of linear approximation is using the tangent line to a point A on a function to approximate y values for the function near to A. As you can see in this graph, if you find y values for x is close to where you approximated, the y values are fairly similar to those on the curve. However, if you calculated for an x value far away from the point of approximation, say over here, you can see that the y value you would find would be pretty far off from the actual value on the curve. In this way, the accuracy of your approximation depends on how closely your a value and your x value are on the curve, and this can vary from function to function. Some practical applications of linear approximation is solving problems without a calculator and simplifying the process of finding y values for ugly x values in a difficult function. So to understand linear approximation and to start using it in your calculations, you must first understand the general formula we have here that we use for linear approximation. So in this formula, we're essentially finding the tangent line to a point A, which is easy to find for the curve. And then we're kind of manipulating the equation to find points close to it. So here in this equation, we start with f of a, which is the y value for the point A for which we're approximating. And to that, we add the difference between x and a, which would be this length right here, times the slope immediately at a. So that would be kind of this length given this slope to find y. So if you take a look at it, it makes sense why this formula would be so accurate and so useful in approximating y values. Taking another look at this formula, you can see that linear approximation requires some prior knowledge of derivatives and basic derivative rules regarding how to find derivatives for trig functions and inverse trig functions, power rule, and pretty much all the basic rules of derivatives. So in this practice problem, we've been asked to find the linearization L of x for the function f of x equals x squared plus 1 at a equals 3. And then using this linearization, approximate f of x for x equals 3.01. So to begin by finding the linearization, we should find the value f of a for the function. So f of a equals 3 squared plus 1, which would equal 9 plus 1, which equals 10. Next, we must find the derivative of the function f of x by using the power rule. So here you can see x squared turns into 2x and 1 into 0. So the slope is 2x. Next, we must find the slope of the function at a. So we just plug a into x and get 2 times 3 equals 6. Now with these values, we can fill in our equation for the linearization. So here we got L of x equals f of a, which equals 10, plus f prime of a, 6, times x minus a, 3. Now we could simplify down this equation, but since we are finding x equals 3.01, it's convenient to just plug it in from here. So then we can see that L of 3.01 equals 10 plus 6 times 3.01 minus 3. We can then subtract and reduce it down to 10 plus 6 times 0.01. We can then reduce and find that f of 3.01 equals 10.06 using linear approximation at a equals 3. Now let's try a problem that's a little more practical use. Here we can use linear approximation to find a cube root of a number that we don't know off the top of the head. So to begin this problem, let's write a function that represents this value. So a function that would accurately represent this could be f of x equals the cubed root of x. Now we want to find an a value that would be easy to approximate a cube for near 26.9. Now the first a value that comes into my head is 27 because it's easily cube rooted and would make a good starting point for this equation. So now we can begin by finding f of a and f prime of a to begin plugging into the equation. Here, f of a equals the cubed root of 27, which would equal 3. Using the power rule, we can find that f prime of x equals 1/3 of x raised to the negative 2/3. Now we can find f prime of a by plugging a into the derivative of x. We can find that a equals 1/3 times 1/9 or 1/27. Plugging these values into our formula for linearization, we get 3 plus 1/27 of x minus 27. From here, we can plug in 26.9 to get 3 plus 1/27 times 26.9 minus 27. From here, we can just simplify and find that 3 plus 1/27 times negative 0.1 equals 2.996. In this way, linear approximation provides us a means of finding cubed roots of unmanageable numbers. Some common mistakes when using linear approximation include issues finding L of x, meaning derivative errors and problems finding f of a in particularly difficult equations, and inaccurate values caused by a drastic difference in the graph between x and a, causing your approximated y values to be above or below the actual y values. That about wraps it up. To summarize, in this video, we discussed what is linear approximation, its uses, went over some practice problems, and discussed potential sources of error. Good luck and happy approximating.